Hi, welcome to the ALICE experiment. We are now about 50 meters underground and I'm standing in this huge magnet where the ALICE detectors will be installed. And it will all happen just below my feet when atomic nuclei traveling at nearly the speed of light will smash into each other to generate what you might call a mini Big Bang. Indeed, we are going to create temperature over a small volume of the size of an atomic nucleus, which will exceed by 100,000 times the temperature in the core of the Sun. And the purpose of all this experiment will be to study how elementary particles are organized under the action of one of the elementary forces of nature, the strong interaction.
Hosted at CERN, the European Laboratory for Nuclear Research, the ALICE experiment involves an international collaboration of more than 1,000 physicists, engineers, and technicians from 30 countries. Together, they're contributing to the resolution of one of the latest challenges in fundamental physics, recounting the birth of matter. Leucippus and Democritus claimed that matter consists of an infinite number of extremely small particles, or atoms. 24 centuries later, contemporary science has proven that the atomist hypothesis was right, initiating the exploration of a new world populated by nearly invisible elementary particles and governed by the unusual laws of quantum mechanics.
We are in the LHC tunnel, the last stage of the CERN accelerator complex. It consists of an assembly of superconducting magnets which are kept at a temperature so low that it will be the coldest spot in the universe. It forms a ring 27 kilometers in circumference, along which particles traveling in vacuum pipes will be accelerated in opposite direction at nearly the speed of light and will collide at very specific locations. Now let's come to the basics.
In normal matter, the most elementary constituents are quarks. They stick together in groups of 3 to make protons and neutrons. Protons and neutrons compose the atomic nucleus. By adding electrons, which orbit the nucleus, one gets an atom. In this way, all the diversity of matter in the universe, with some exceptions, is generated from 2 kinds of quarks, the up and down, and the electron. But there are more than just 2 quarks and the electron. Additional elementary particles such as the strange, charm, and beauty, and the top quark existed only shortly after the Big Bang. The surviving quarks were permanently glued together into protons and neutrons by another type of particle appropriately called the gluon, which transmits the strong force. Now physicists are recreating them in particle accelerators. As the universe cooled, these additional particles decayed into other particles. By colliding nuclei, physicists will follow the reverse path. The very high temperature will untie quarks and create the quark-gluon plasma, where quarks and gluons roam freely, just as they did during the Big Bang. In other words, we will look into our most remote origins. The ALICE experiment consists of a set of highly sophisticated electronic devices which record the passage of particles by delivering electrical signals, which in turn are converted into a digital signal ready to be processed by computers. ALICE uses all known particle detection technologies to track, measure, and identify any kind of subatomic particles' momentum and energy in 3 dimensions. Since these particles are too small, even for the most advanced microscopes to see, these measurements act like a fingerprint and let physicists know what is happening.
A major challenge of ALICE will be coping with a staggering amount of data. Millions of particles will be produced every second, but only a few thousands of events are interesting to physicists. A large computer farm of several hundred PCs will decide in a few seconds whether the event is interesting or not.
Despite the selection of only a small fraction of the events, the amount of data collected after 1 year will be the equivalent of the amount that can be stored on a stack of compact disks more than 4 kilometers high. Data are archived in the CERN Computer Center before being distributed across the world. The data exchange and access is organized through the next generation of World Wide Web known as the grid. This fantastic new tool will provide any physicist with the computing power of millions of computers. While advancing mankind's fundamental knowledge of the universe is the main goal of ALICE, there are more practical benefits to physics research. More direct offshoots of high-energy physics research include cancer detection and treatment, as well as medical imaging techniques such as PET and MRI scans.
This is the end of our journey. The gigantic ALICE experiment and LHC accelerators are on the tracks to explore the fascinating world of the infinitely small and unveil some of the mysteries at the origin of our universe.